Hello, everyone, and welcome back to the 2018 Hack Summit. We're privileged to be here with Eli Ben-Sasson, who's a professor of computer science at Technion, which is an Israel Institute of Technology, and he also was the co-founding scientist of ZCash, which is a privacy-preserving cryptocurrency, and he's also the co-inventor of zk-SNARKs and the co-founder of Starkware, which is a new startup that's going to be helping existing blockchain solutions to scale to larger degrees. And he also has a new technology called zk-SNARKs, which they have also invented within Starkware. And they're going to be talking about all these technologies today. And Eli, it's such a pleasure to have you here. Thank you so much for being with us.
Thank you, Ed. Thank you so much. It's really, I'm excited and honored to be here. It's the first time I'm doing such an online event. So thanks very much for having me.
Yeah, we're lucky to have you here. And audience, if you like what Eli has to say here, please click the donate button on the bottom of your screen. You'll be helping out a lot of important nonprofits in the coding space, like Women Who Code and Black Girls Code, that we're raising for at Hack Summit this week. So Eli, I really want to commend you for joining us and taking a stand for these coding nonprofits together. It really is going to make a difference. And so we're ready to learn from you. So please feel free to kick it off and maybe tell us a little bit more about your background. We'd love to get to know you personally before you dive into the presentation. Maybe how did you get into software? How did you get into programming and math? What inspired you originally? Give us that context about you personally.
Yes. Okay. So I guess it's too late to say that I never really got into software, and even today, I'm a really shitty coder. So but I'm involved in software. Okay. So about myself, I'm Israeli. I started off studying theoretical computer science and math. And I finished my PhD in 2001, got it from the Hebrew University in Jerusalem, and then went off to MIT and Harvard to do my postdoc. And there I got involved in very interesting mathematical questions, foundation of computer science, specifically something marvelous called the theorem about probabilistically checkable proofs, or the PCP theorem. And it's a fabulous theorem that was proven in the mid-1990s and has revolutionized computer science. Mostly it applies to show hardness of approximating combinatorial optimization problems. But it also was noted early on that it also has positive applications to prove computational integrity. So I got into the study of making these proofs a little bit more efficient from a purely mathematical standpoint. And that's how I started getting involved in this area. Then at some point later, I received a sizable grant from the European Research Council. I was already back in Israel, a professor at the Technion. And I didn't quite know what to do with it, but I thought it might be nice to start programming, this more efficient version of the PCP theorem. And that's how I got involved in software development. Fast forward, at some point, it dawned on me, quite surprisingly, that the best way for applying this kind of technology is within the permissionless blockchain world. And that's how I became involved in things like ZeroCash. That's how I got to where I am, where this thing that started off very theoretical became something more practical.
Great. That's very helpful, Eli. Thank you for that background. So why don't you go ahead and start up your presentation. Go ahead and load up your slides and share your screen. And while you're doing that, audience, I'm going to start polling so that we can learn more about you while Eli prepares his presentation. And I guess the first question I'll ask you is, do you know what a zero-knowledge proof is?
Yeah, and Ed, if you because I only see my slides now, so if I'm going too fast, too slow, or if the audience actually wants to dig in deeper to some things or wants to back up a little bit, please let me know, okay? Because I don't see the chat screen.
I'll tell you the results as they come in, and so far we're already getting votes, and it's about most people do not know what a zero-knowledge proof is. I would say about 2/3 of the audience do not, whereas 1/3 does. So we actually have. Actually, it's impressive that even 1/3 of them do know that. So I commend you, audience, for being so informed coming into this.
Great. So So yeah, I'll cover what a zero knowledge proof roughly is. Okay, and this is the presentation that I use to explain what I'm doing. And as you can see in it, I'm affiliated with ZCash, with Technion, and with Starkware, which is our new startup that I co-founded. I'm chief scientist of it, and currently that's my full-time job. Okay, so a brief history of money. Human beings have this amazing ability to reach consensus on forms of money. And it's a very mysterious property, but we all benefit from it. So in early days, it was some physical resources that were limited by nature. In my own elementary school, money during winters was in the form of wrappers of gum. And it's said that in prisons, it's cigarettes or stuff. Okay, so humans have this capability. And we're all accustomed to money which is controlled or limited in supply by decision of a central trusted party, like a king or a central bank. But we're also, I guess, now aware that cryptocurrencies do it differently. They don't have a central trusted party. Rather, they trust in crypto. And the limited supply of this money system is limited by consensus. Okay, so there's no trusted party. And the innovation of things like Bitcoin, I mean, Bitcoin was the first, was that it's the first time that a societal function, something that we all need and rely on, that we thought would require a trusted party, is suddenly replaced by some mixture of algorithms, protocols. And this is truly amazing. So Bitcoin did it with fiat money, but you could also now ask, maybe it will go to other places, law, corporations, academia, religion, government. So who knows where the puck stops. Now, when you remove the trusted party with a bunch of algorithms, you create a new problem, which is computational integrity. So what does it mean? It means very simply, how can the public trust the output of a computation? You know, if I say that the computation outputted 42, how can you trust me? And often the party that executes the computation is actually incentivized to misreport the output. You know, if I need to report my taxes, I have some incentive to report a lower amount. I might offset that incentive by my fear of being, you know, sent to prison if I cheat, but there is some incentive to misreport the output. And the larger the party and the more powerful it is, then the larger the problem, right? So Bitcoin's solution is rather simple. Everyone sees and checks all transactions, and that's how you establish public trust. But this raises two new problems. One is privacy, and the other is scalability. So we should recast the problem. How can the of computation in a way that is both scalable and preserves privacy without a trusted party that you rely on? And there's a marvelous answer that now I want to explain to you. And these are called zero knowledge proofs. And in general, the whole area of modern proof systems that was, you know, in 1985 in a marvelous paper by 3 researchers. 2 of them received the Turing Award, the highest award in computer science for this work. So this has been cited in thousands of papers, and it's a really remarkable contribution. But only recently does this technology start getting its full potential implemented. So now I want to explain to you what a zero knowledge proof is, but I won't give you a mathematical definition. I rather would like to explain to you from a functional point of view. What function does it serve? What can it be analogous to? Okay, so the analog is just a grocery receipt or the kind of bill that we get in a restaurant. What is this receipt? It is a string of characters that proves to us that we should pay the total sum. Okay, and the reason this is a proof of computational integrity is because both parties, the grocery owner and we, know that we can recompute the total sum and check that it's okay. By the way, Ed, how am I doing? Because I can't hear any feedback. So
you sound fantastic, and I think we're really enjoying it. Keep going.
Okay, good. So a proof is like a receipt, right? It's a string of characters that establishes computational integrity. That's it. There are a few interesting differences. First of all, zero knowledge means that the proof, the string of characters, does not reveal any information about the inputs that went into the computation. So in this case, you could think as if the sums are blinded out, as we often see in, in television shows where they want to blind out some of the inputs. So think of a receipt that looks like that. We only see the total sum. And nevertheless, we are certain that the computation has been done correctly. Another interesting fact is that you can get these proofs for any computation, not just for summation of numbers as here. And the next thing that is very, very important is scalability, which means the following thing. So scalability is this sort of trade-off between the time it takes to generate the proof and the time that is required to check it. And here is something extremely remarkable. So if t is the number of cycles it will take to naively do the computation, then scalability means the combination of two things simultaneously. Scalable verification means that the time needed to verify the computation is exponentially faster than the time needed to execute it naively, exponentially faster. So we go down from t steps to something like polynomial in log t with a very small exponent in the polynomial, like log t squared, okay? And simultaneously, we also have scalable proving complexity, which means that to generate the proof that can be verified in this sublinear logarithmic time, the proving time does blow up, but by a rather small factor, only by a polylogarithmic factor. So this is called quasi-linear. So you can't generate the proof in t steps, but you can generate them in t times log of t to some power. So just to give some numbers, if the number of steps is a peta, 2 to the 50, then log squared of t is 2500, which is much less than a peta. And t log t is larger than a peta, but only by a factor of 2500, okay? And this scalability is extremely important in the context of blockchains because you can use proof scalability to solve and address blockchain scalability problems. For instance, if the latest Bitcoin UTXO set, which for those of you who are not familiar with Bitcoin, just think of it as the latest state of the system. So like this is, all the addresses that currently hold funds and you can use them to pay to others. So let's suppose that verifying the latest UTXO by going over all of Bitcoin's blockchain from the Genesis block in 2008 up till today, let's suppose it would have taken 1 peta steps, which is roughly what it should take, give or take a few magnitude. Then we could have one day, and this is what Starkware will deliver one day, you'll have a single prover that spends more time, 2500 times 2 to the 50 steps, and posts a proof that attests to the computational integrity of the latest UTXO set being consistent with the very long blockchain. And then everyone else can verify it, say on their smartphones, in 2500 steps, okay? So when people talk about scalability issues in blockchain, they should remember that SNARKs, that the zero knowledge proofs that we're delivering could be a solution to that. Okay. As I said at the beginning of the talk, my research is about scalable proof systems with concrete efficiency rather than asymptotic, efficiency. And in 1995, I was still a teenager back then. It was I was not a teenager, but I was in university doing my undergrad studies. So back then, people already knew how to get zero knowledge with scalable verifiers. But the prover was a galactic algorithm, meaning that, like matrix multiplication, fast matrix multiplication is something that works, it pays off only for extremely large input lengths that may be larger than the number of atoms in the universe. And over the past 30 years of research by many of my colleagues, and myself, we managed to bring it down to something that actually runs on a laptop. I'll show you a demo soon for meaningful computation. And this uses scalable versions of the PCP theorem and an interactive variant of it called interactive oracle proofs. I just want to acknowledge that my work here that I'm describing has been going on for very long, and I have a lot of amazing collaborators that I'm very grateful to. So here's a list of them. Now, how did I come to be involved in things like blockchains and ZCash? So I started off doing moon math. I think Greg Maxwell was the first to coin this term. It's the analog of rocket science in our world. And in 2008, I started implementing PCPs thanks to this generous grant by the European Research Council. And in 2013, we had some preliminary code working, and I gave a tour of talks at universities mostly, trying to explain who would use it. And in hindsight, what happened there, and it actually happened at the Bitcoin San Jose conference in 2013, which was a very magical conference to attend. What happened was that we realized the following thing, that when you talk to people who are familiar with a conventional model, banks, Google, Facebook, when you explain to them what a computational integrity proof looks like, they'll ask, well, what is zero knowledge? Who proves what to whom? And why do we need it? Like, will my bank prove to me that it is handling my funds correctly? Never did this. Why? It's being audited, regulated. Why should it do it? Should I prove to my bank that I am handling my funds correctly? It's unnecessary. The bank anyway sees everything I'm doing. So who's going to prove what to whom? So they would ask, what is a zero knowledge proof? What is a proof of computational integrity? Why would you use it? And the decentralized folks, the Bitcoiners, the Ethereum folks, the Zcashers and whatnot, they will ask, okay, where's the code? Can we use it? Don't tell us what we can do with it. Here are 5 problems that we would want to solve tomorrow if it's efficient enough. And this led to my being a co-author of this academic paper called ZeroCash that shows how to use zero-knowledge proofs for getting more privacy and fungibility in decentralized blockchains. And then all of us 7 scientists partnered as founding scientists in this company, the ZCash company, that converted the academic grade code into a working protocol that is live now, and that's the ZCash cryptocurrency. So this was 2015. And I have new technology that I want to share with you called the zk-SNARK, and a new startup, Starkware. I should also point out that we're hiring, so if you're an exceptionally good engineer with a strong background in mathematics, then please talk to us. I should point out that we are located in Israel, but if you think this is relevant to you and you're exceptionally good, please write to us through our website, which is starkware.co. Okay. So let's see what zero-knowledge proofs do in the context of ZCash. So what is the problem that we solve? In Bitcoin, Alice uses some crypto ID, like this red sequence. And Bob has his own crypto ID, like this blue sequence. And then when Alice pays Bob, then the transaction pretty much looks like this. So address of Alice, address of Bob, and the sum. Good. But this transaction is posted on the blockchain forever. And Bob must use his same blue crypto ID when he pays off someone else. So this means that with a browser, Alice can see when Bob used the funds and how much he paid. And if he bought coffee at a Starbucks and Starbucks doesn't want to change their address every day, Alice can learn that Bob bought a coffee. Similarly, if Alice is an employer and she employs both Bob, then when she pays them on the 1st of the month, they can each sort of see that the same address had 2 transactions and they can compare their salaries. So from a high-level point of view, Zcash's solution to this is to encrypt the transaction. Actually, you post a commitment to them. And then what everyone sees on the blockchain is sort of just this sealed envelope that contains the digital analog of the sealed envelope. So actually solving anonymity is very easy. What's hard is computational integrity, because maybe inside this envelope I just printed money and paid myself a large sum. To solve that, you append a proof of computational integrity. And the particular version of zero-knowledge proofs used by Zcash are called zk-SNARKs, okay? And this is a really great technology. You know, I just heard, I guess a lot of you heard on Twitter and other places that Sergey Brin, you know, said that he's amazed that this zero-knowledge, mind-boggling technology is entering the world, and that has actually been deployed by a company in such a short time frame. So this is thanks to the marvelous ZCash engineers and scientists led by Zuko. And the zk-SNARKs are extremely powerful. So they have very short proofs, less than 300 bytes long. They can be verified extremely fast, less than 10 milliseconds, and they are universal and Turing complete. So you can apply them to any computation. And for instance, as we're speaking, the ZCash engineers are diligently working on a new version of the that's going to be released in November, and it will have much better functionality. And you can achieve all of that with the same technology because of the universality of zk-SNARKs. But the problems with these zk-SNARKs are that they require a trusted setup that is very hard to properly administer. And compromising that trusted setup can leak a trapdoor that can be used to forge money. Also, quantum algorithms can efficiently compromise this trusted setup and find that trapdoor. Just a little bit about ZCash. This is, not updated, but you can just Google and see price goes up, price goes down. Anyways, so what is this new proof system that we have? It has a scalable proof generation and verification. It is transparent, which means that there's no trusted setup. All the randomness that goes into setting up the system is public randomness. Okay, and this is a key property. It's also post-quantum secure because it doesn't have any number of theoretic assumptions that back its security. Okay, so why is transparency important? It's important for ongoing public trust. There exists a trapdoor. I mean, it exists. Maybe no one knows it for any given SNARK, but if it is found once or leaked out or compromised, then a huge catastrophe could happen. And with a STARK, you just don't have such a trapdoor. Another thing is that when you have this open source environment and a lot of collaboration, you would like, once the code is done and reviewed, you would like to be able to use it. And with a zk-SNARK and its trusted setup, you would then have to trust yet another phase after code review and auditing, which is that of generating the keys. And especially if you go to extremely larger governments or big corporations, then we all should have reason to doubt whether when they say that they generated keys in an orderly manner and did not keep any backdoors, well, that's going to be hard to trust, frankly, right? So I just want to give you some example of code that we actually ran, and this is for the following problem. Suppose the police has posted a commitment to the state of forensic DNA profiles. So, the police collects DNA profiles from all over the, whenever they find stuff in crime scenes, and they maintain this database. Okay, it's of course a privately maintained database. Now, suppose that the police would like to prove to the public that, for instance, the president-elect's DNA profile does not appear in that database, right? Without revealing the database, will the public trust it? So we actually wrote proof of concept code, which is part of the libstark code base that I'll show to you in a second, and I'll just run this simple example. We wrote this Stark prover and Stark verifier that prove the statement that basically I went over all the database entries for which I committed previously, and I checked for a match with this other DNA profile that I just commit to, and I don't tell you what it is. And the answer is what I claim it is. There's a there's a high quality match, a low quality match, or no match at all. And I just want to say that it is not quite a set membership testing. It's not just about asking, does this string appear in that big database? It's slightly more complicated than that. You have to check, things like edit distance between the profile and any given profile that appears in the database. So going back to scalability, let's see if we can actually, make meaningful progress here. So you can look at the ratio between the time that it would take to verify a proof using a Stark, divided by the time it would take to verify the proof naively. Like if you take the Chief Justice and give him access to the database as an auditor and ask how much time would it take for him to verify this. And you can look at this as a function of the number of entries in this database. You can similarly look at the space ratio. So you could look at the communication complexity or length of the Stark proof divided by the size of the database, because that's also a proof for the computational integrity of the statement. And once either of these ratios goes below 1, it means you get meaningful compression. It means that the Stark verifier is either running faster than naive verification or is consuming less information than what would be needed for naive verification. And here are plots that we're very proud of that show that we actually managed to break the compression bound both for time. So we managed to generate proofs for which verifying them was faster than doing the naive verification, and similarly with proof length. So the generated Stark proof length was significantly smaller by a factor of roughly 100 than the length of the naive information. So if this would have been a blockchain, you could compress, let's say, factor 100 blocks, and this is in the academic grade code that was just a proof of concept. And Starkware will have an engineering effort that will probably push this compression down. So we plotted here what would happen if we could generate proofs for larger and larger data sets, and you can see that the compression factors get more and more impressive. But the sort of circles here represent those input lengths for which we could also generate a proof. Okay. Now, I just want to say that there are many, many other systems out there that you probably heard of, things like SNARKs. I just mentioned them. Bulletproofs, but there are other systems like Ligero, which is based on secure multi-party computation. There is a system based on interactive proofs called Hyrax. So here what I do is I just want to show you how they differ in terms of their asymptotic properties. So you can look at systems that have proof of scalability, meaning quasi-linear running time, verifier scalability, which is polylogarithmic running time, transparency means only public coins, post-quantum security roughly means that the security assumptions do not rely on any number theoretic assumptions. So no elliptic curves, no RSA assumptions, no Diffie-Hellman. So as you can see, ZK starts from a purely asymptotic and assumption point of view, offer pretty good benefits that are not obtained by any of the other existing systems out there.
This is great, Eli. Let me jump in and ask a couple of questions here, so that we can make sure that the whole audience is up to speed and is kind of on the same page. So might be helpful for the audience who may not be as mathematically inclined. Maybe would be if we could try to explain a ZK-SNARK or a zero-knowledge proof using maybe an analogy. Like I've heard that this cave analogy being used pretty often, or a Where's Waldo analogy. Any of those on hand that you might be able to help the audience who just may not be as up to speed on the math side of things?
Yeah, so I mean, I could give the Waldo and the cave analogy. They explain the mechanics of how a zero knowledge proof is generated. It's by this interactive protocol. I think a better analogy in our case would be to refer to, because this is actually the way we achieve zero knowledge, would be to refer to Shamir's secret sharing algorithm, right? So suppose I have a secret that I would like to share among 50 people, so that if all 50 of them join together, they can reconstruct the secret, but none of them, or no 49 of them, can do it by themselves, right? So, yeah, sorry, let me simplify it. Instead of 50, let me make it, suppose I want to share a secret between between 3 people, such that any 2 of them can reconstruct it. Okay, let's take a simpler example. Okay, because the math is going to come out simpler. So what do? I give the 3 participants 3 numbers, 1, 2, and 3. And then what I do is I think of my secret as a number that is a point evaluated at 0. So like, right? And then what I do is I pick a uniformly random other point, let's say 4, and then some random number. And then I have this line that goes through the secret at 0. And let's suppose that the random number I picked is 10. So there's a line that goes through 0 in the secret and through the point 4, 10. Okay. Then to each one of the participants, I give the evaluation of this line at, player number 1 gets the evaluation of this line at 1, player 2 gets the evaluation at 2, player 3 gets it at 3. Okay. So now, player number 1 by herself just got this completely random number. Player number 2 got this random number. Same thing for player number 3. But if any 2 of them meet up together, they can interpolate the line going through those 2 points and find out the secret, right? So let's take a step back and see what happened here. What happened here was that the dealer committed to a secret, but did it in such a way that a partial view that sees only 1 out of the 3 shares gains no information. Okay? This is exactly how we get zero knowledge in our case. So instead of taking a single, our secret would be, I'm waving hands here, but roughly what we do is like this. Our secret is the full execution trace of the computation. Or rather, to be more explicit, what we do is we take the execution trace of the computation, which would prove to you that the computation is correct, right? This is the analogy of the receipt, right? Of the grocery receipt, right? The grocery receipt specifies a full execution trace of a summation computation. So think, your starting point would be a full specification of the execution trace of your program, right? How the registers get added up and then, move to the memory and back, right? This very long sequence, right? That's our starting point. Each one of these states, think of it as a number. So if we have t steps, we have t numbers, okay? And we're going to commit to those t numbers. Now, if you get to see any one of these t numbers, you'll be gaining information about the program, which is bad. This will be revealing zero knowledge. We want to prevent that. So what we do is we sprinkle a little bit of salt or randomness, right? So we take another, let's say, 100 more random numbers and just append them to the execution trace. Okay, so now we have, let's say the execution trace was 1,000,000 numbers, and we added 100 more. So if you get to see any of the first 1,000,000 numbers, that's going to be bad. You'll learn something about the computation. If you get to see any of the 100 numbers, or even all of the 100 numbers, you learn nothing about the execution trees. Okay, so now we take these 1,000,000 and 100 numbers and we mix them all together using an error correcting code. Specifically, we take an evaluation of a polynomial that interpolates all of these 1,000,000 and 100 numbers. But we evaluate that polynomial not on the points that we started with, but we evaluate them on the points, let's say, between 1 billion and 10 billion. Okay, so we evaluate this whole thing elsewhere. And the fundamental properties of polynomials in algebra now imply that if you see any 99 numbers from that domain, you learn nothing about the original execution trace. Sort of the randomness gets mixed in to the whole thing. So this is, our start proofs work exactly like that. We take the execution trace, we add randomness to it to sort of we evaluate it on a different domain. And then our prover commits to this information via a Merkle tree. So basically, it's like the secret sharing analogy, but instead of having shares dealt to 3 players, the prover is committing to all of the public via one Merkle tree to the whole batch of information. And then later on, after the prover has committed to this information, the prover gets public randomness. This is why the system is transparent, and opens up a few locations, but less than 100 of them, and you know, argues about that. So this is roughly how we obtain zero knowledge. We use something analogous to secret sharing, to what is called Shamir secret sharing. Okay, this is a technique invented first by the great cryptographer Adi Shamir, the S in RSA, and it's extremely useful. And that's the kind of privacy preservation that we use in our SNARKs.
That's very helpful. Thank you. So I think about half of our audience is now understanding the basics of what you're talking about. There still is a few audience members I'm seeing in the chat that might need some additional clarification who may not be as deep into the technology. Would it be okay if you walk through maybe the cave analogy or the Waldo analogy for those audience members, just so that they understand at the kind of basic level the idea of zero knowledge at the high level?
I mean, I could do that, but and I empathize with the desire to understand the magic in zero knowledge. I'm not like. I'm not sure it would be the best use of my time, in the sense that I haven't prepared this kind of explanation, and I'll probably do a bad job of so I mean, there are probably public talks out there by video that will do a much better job than if I try to do the Waldo example or the cave example. And I mean, I deeply apologize to those online listeners that you know, that would like this kind of explanation. I just didn't prepare for it, and
that's fine, no problem at all. Our audience understands. I'll try to give like a pretty terrible explanation of it. It's not very good, but
okay.
But essentially, like, have any of you guys in the audience ever played Where's Waldo? We have to find the cartoon Waldo in a picture, and there's like this big, colorful, jumbled picture of all these cartoon guys, and there's a Waldo character somewhere in the picture. Well, if I show you that picture and I point out where Waldo is and I identify Waldo, then I'm also showing you where Waldo is. And so I'm not just proving that I know where Waldo is, I'm showing you exactly where Waldo is in the picture, which means I'm revealing the solution to you as well, which means I'm violating the data privacy of the system. And so, you know, that is not a proper use of privacy and preserving that knowledge. Now, if I instead had like a black overlay of the Where's Waldo picture, and I could maybe move this black overlay around and show you this little cutout that showed Waldo and nothing else in the picture, then you would know that I knew where Waldo was without showing you where actually Waldo was. So I'd be preserving the privacy of the system. So, you know, hopefully that makes sense to you for those of you who might not be at kind of the same level of the rest of our audience. But, you know, Eli, I want to acknowledge you for explaining that, because that did really help the audience with that analogy with 100 random numbers. And I think now our audience should be more up to speed. So let's go to the audience. The audience has a few questions for you, and it's been really interesting. So Bichad asked a question here, which is, thank you for the very informative talk. Quick question about ZCash. Is the post-quantum security aspect that you spoke about already implemented in ZCash?
No, it's not. So ZCash right now is using zk-SNARKs. It's using it for the first version of the circuit, which is called Sprout. And it's also using it for the next version of the circuit, which is called Sapling. And I don't know about, you know, what are the plans later on to address post-quantum security. I guess, you know, this is a question better addressed at the leaders and engineers of ZCash.
Great, thank you, Eli. Next question is from CryptoMoon, which is, what is the business model of Starkware, and which projects will implement SNARKs first?
Great question. Okay, so the business model of Starkware is to Okay, we would like recurring revenue, and we believe, okay, as I said, the SNARKs can deliver two aspects. You can want one of them, you can want the other, you can want both. One is privacy, which is similar to what SNARKs give you in ZCash. The other one is scalability, which is something that no other technology currently delivers as well as SNARKs, which is the ability to compress a very long computation on behalf of the public in a transparent way with no setups and no keys needing to fly around, and in a very efficient manner. So for instance, our Stark prover is 10 times faster. The academic grade code is 10 times faster than the second fastest technology for generating proofs. Good. So it seems to us at Starkware that scalability is much more of a fit in terms of a business model, because there's huge market demand for scalability solutions in the blockchain space, right? Getting the 10 transactions per second of Bitcoin and Ethereum and whatnot up to the 2,000 per second that Visa can process, and the 250,000 per second that Alipay processes. So for that, we're going to need a whole lot of tools, and I think SNARKs can really be beneficial in this aspect. Let me explain how. So instead of having everyone see every single transaction, you could have a node processing many transactions and publishing a proof that an update to the state of the system can be accepted. Crucially, no one needs to know or trust that aggregator, right? Because it's just like you don't need to trust a miner. You can verify and see that the mining worked out correctly. So with the Stark proof, everyone can verify it, and there are no trust assumptions. Good. So at Starkware, we believe that scalability is going to be more valuable, and we're going to address that. And there's several different ways that we can, help the ecosystem. So there are a bunch of angles, things like generating proofs of solvency for exchanges could be very interesting. We could be working with providing infrastructure projects for big blockchains, helping them integrate Stark into their basic infrastructure layer that everyone can use. And I guess things like that are how we believe that we'll move forward.
That's great. Thank you, Eli. Next question is, what is your opinion on Mimblewimble compared to ZK-SNARKs? Would it be possible to integrate this into ZCash?
Possible, everything is possible, right? The question is whether you would want to do it and whether it's beneficial. So if I remember correctly, I think Mimblewimble is transparent, but it doesn't have the scalability of SNARKs. And so like the verification time, I believe, works scales linearly with the size of the computation. And also, if I remember correctly, I think that Mimblewimble is not universal, right? I think it only works, for something that's very specific. So I think that probably, again, this is a question that is better, asked to the ZCash leaders and engineers. But I think that because of universality, lack of universality, you probably wouldn't get enough functionality from Mimblewimble. That would be my answer. But I confess that I haven't studied Mimblewimble in great depth, so I might be wrong about its universality. But I think it's not universal. I think it just does. It doesn't have full functionality, I think.
Thank you, Eli. Luminous asks, this is kind of a funny question here. Was the Starkware name influenced at all by Tony Stark, aka Iron Man?
In hindsight, so okay, the way it worked is the name Snark, of course, was deep. And actually, it was a public talk at Stanford that just before that, I don't know, it like sort of dawned on me this name Stark. And and I remember like presenting the audience. There were like 400 people in the crowd. And I said, we have this new thing. So would you prefer calling it blah, which I don't remember right now? And there was like, or would you like Stark? And the image I had there was, of course, the Game of Thrones, Ned Stark and House Stark and so on. And there was a huge, huge acceptance. So basically I said, okay, Stark it shall be. Later on, we learned, and this, I didn't grow up reading comic books in America. So later on, we learned that, of course, that Stark Industries is where Iron Man works. He's the CEO of Stark Industries. So we are called Starkware Industries, and that's sort of homage to that. I should credit, so Zuko, the CEO of ZCash, pointed out the Stark Industries. So apparently he read more comic books, at the right age.
That's great. Mitchell asks, I've heard Starks currently have challenges with RAM usage, memory usage. What's the current status?
So I think it's a misconception. What happens is this: Starks are good at scalability. So we really ratcheted it up and, did like really large computations. And then you reach RAM things. But I mean, if you want, I can just show you like, shall we just run something quickly at Stark?
Go for it.
So I'll just screen share a little bit. Let me just go back here and screen share. Okay. So I am using the application window. Okay. So I am using a T480. Okay. So it's one of, I bought it like 4 months ago. It has, I think, a quad core maybe. So here's can also download this, and so here I'm running computation with a Stark. So it's generating the witness. And for some reason, whenever you try to do something online, of course, it takes a lot more time, which I think is probably due to the video or screen sharing or something. Meanwhile, while it's running, I can show you what happened when I executed it without doing the screen sharing. So the prover time took 7 seconds. The verifier time took 60 milliseconds. The proof oracle size was 4 gigabytes. So the RAM consumption was much less than 4 gigabytes. And what is this computation? This is a computation of the DNA sequence checking. So now it took 20 seconds, but still the RAM consumption is small. So again, I think that the big RAM consumption is just because my computer is actually active with doing this video. This computation would be similar to, it's the same thing as a single ZCash transaction. Okay, so the RAM consumption here is going to be similar, or actually better than what you'd get with Starks or bulletproofs. Let me just show you, just a little bit. Wait, I need to screen share a different screen. So I'm going to stop sharing. And then I will share a different screen. And the screen I am going to share is, I think, this.
By the way, while you're sharing this, I just want to make a comment, which is that I just think it's super cool that you're actually demonstrating RAM usage in real time to answer this question about RAM usage supposedly being too high. Very.
I encourage everyone to go to the libstark GitHub, download the code on your computer, and run the tests. And you can do htop and see how much computation it takes. So let me just show you some. These are some of the latest measurements that we've done compared to all the other latest and greatest proof systems. So let's first of all look at this running time. What's happening here is, so you can see the Stark, prover time. So many of the other systems, bulletproofs among them, Ligero, have so far been implemented only in single thread. So here we're just comparing libstark in single thread to these other systems. And you can still see that it's the fastest there. Now, when you allow multi-threading, so you can see that libstark is much faster, as I said, at least 10 times faster than the second fastest, which is actually libsnark. Now, as you can see, so we executed all these systems up to the 10-hour benchmark. And what happens is that over here, of course, you're going to use quite a lot of RAM. But if you look at the other, they just can't reach that high. But I assure you, they will also have serious RAM problems when they try to reach, you know, something like a circuit with 2 to the 35 gates, right? There's no doubt about that. So the misconception is that if you take SNARKs and try to execute them, you know, at their limit, which no other proof system can achieve, then yes, you're going to encounter RAM problems. But any other system will encounter the same RAM problems and worse. Let me explain why. All of these systems out here use an FFT. SNARKs use one FFT over very small fields of size, you know, 32 bits or 64 bits, and then they just hash it. All the other systems do an FFT over a cryptographically large field with 256 bits or worse. And then after that have a very heavy cryptographic operation, usually involving elliptic curve cryptography. So their RAM usage at, you know, head to head, I'm guessing will be larger than that of SNARK. But again, you're more than welcome to download libstark, libsnark, you know, bulletproofs, measure it on your own computer and check out the RAM consumption. For small head-to-head on the same computation, I'm very confident that SNARK will do better. You can also see here, you know, verification time. So as you can see, verification time for SNARKs is pretty small. It is larger than the post-processing time for a SNARK by a factor of 10, but the pre-processing of a SNARK, the trusted setup, you know, is super linear and goes to, you know, several hours for these computations. Bulletproofs have very short proofs, but their verification time scales linearly with computation size. And here you can see the proof length, in which in SNARKs it is on the order of hundreds of kilobytes. By the way, we've brought it down by roughly a factor of 10. Thanks to our marvelous engineering team at Starkware. And, you know, we'll probably bring it down a little bit more with hopefully some new science and engineering. So, yeah.
Great, thank you for that. We'll take one more question from the audience, from Kartik, which is, what do you think it'll take for the general public to accept that systems using SNARKs actually do what they say? The general public may end up leaning on the reputation of the companies using them, which would be what we use for trust today. So how can we get the world to be comfortable with the idea of data privacy and zero knowledge actually being a credible solution from a political perspective and from a buy-in perspective from those who may not fully understand the math behind it and the proofs behind it?
I would say it would take time, but this is the process that all science, you know, goes through. To the extent we trust encryption, you know, AES, SHA-2, RSA, Diffie-Hellman, and then systems built on them. So, I mean, you know, years and decades of better implementations and, you know, peer reviews and scientific scrutiny of these things is what helps. I think it will be similar here, and it's always, you know, it's not any different. And I'm very confident that these things will be accepted and addressed. I just want to point out that the, you know, the leaders of the innovative and leading cryptocurrencies, like, you know, Ethereum and ZCash and others, they are very open to helping out with this and scrutinizing and looking at this stuff.
That's great. And kind of one kind of question from me here. So if you think about going forward, the applications of SNARKs and SNARKs, just that our audience has something actionable to take away from this, other than kind of helping existing blockchains to improving their technologies, are there other applications of this that our audience might want to play with this for, other potential uses of this, so that on their own, if they're curious and they want to get going with this and they want to play with libstark, what are some examples of ways they might be able to tap into it or have fun with it on their own to start appreciating it?
So first of all, again, I'll just share. Let me just share the you know, libstark. Why can't I find? Wait, Chromium tab. Here it is. Okay, let me share this. Okay, so please, everyone, go over here, you know, and download the code. It's rather simple. You know, you compile it, you know, compile it thus, and then you can start running, these examples and measure them out. And I think that right now, programming new TinyRAM assembly codes, this is for the callets function, you could get it for other things, would probably be time consuming, but you're more than welcome. There is an assembly language that you can try playing with and constructing other programs for. I just want to show you, here there are some examples that you can already start. So here's the subset sum TinyRAM program. You can basically apply it using different opcodes that are specified in the code and see what happens. I should just warn, this is academic grade code, so please don't try to deploy anything using this code. There must be multiple bugs, but it could give you some. So using the examples here and the scripts that we have for testing the system, you can see how it works and then start from there. And send us emails, of course, with questions. We'd be very happy to help.
Thank you, Eli. Well, this has been such a pleasure to learn from you today. I think the audience really appreciated their glimpse into the future of blockchain and how we can make it more scalable. Eli, thanks so much for being here and to take a stand for the nonprofits and to educate us all on SNARKs and STARKs and how they compare to bulletproofs. And it's just been fantastic learning from you. We're very lucky to have your time, and I just want to acknowledge you for being here and to help us. So thanks again.
Thank you, Ed, so much, and thank you to the audience for the great questions. And whoever you're rooting for in the soccer game, I hope they win.
That's great. We'll be right back with Jutta Steiner, who is the former CISO of the Ethereum Alliance, and also she has a company called Parity.io, which we're going to learn all about in just a second. So just stay us. We'll be right back, and thanks again, Eli. Appreciate your time today.